So in the pre-part of this week's lecture, we looked at dimensionality reduction, but that's only one application of unsupervised machine learning. There's another application that's very important, which is clustering. So let's say we had a visitor from another planet who had no idea about the differences between different types of fruits. For example, oranges and apples. Well, knowing that we provided our visitor with the identity that there are two different types of fruits here, without knowing their labels of apples and oranges, we might take them to the countryside to look at different types of fruits and see whether they can make distinctions on their own. For example, by measuring the color of a fruit and its texture, they might be able to plot them in a 2D plot like this one and associate certain samples that they see with one cluster and certain other samples with another cluster. With this in mind, our visitor might be able to label these as fruit type number 1 and these as fruit type number 2. This is essentially the problem of clustering. We're given a data set with m points and we like to create a k clustering, which is a partitioning of the data into k clusters where the cluster assignments are hard, meaning that the union of all of the k clusters would equal the entire data set, and that each point belongs to exactly one cluster. That means the intersection between any two subsets is exactly null. We're going to also say that each of the clusters has a particular mean or center mu k. So given a data set like the one on the right, what we'd like to be able to do is have our algorithm be able to label these points with a cluster membership, meaning one of these k clusters. The output would be something like this, where each of the symbols would have a different color and shape depending on which cluster it belonged to. When we come up with an idea of the clustering algorithm, it's important to have an objective function, like a cost function. So we're going to measure the clustering quality by using this informal definition, that points in the cluster should be similar or close to each other and to the center. This is going to define our error or cost metric as well. We can say that the error within a particular cluster K, or JK, is going to be equal to the summation of the pointwise cost of each individual point. How we measure that is up to us, but for example, we might take a Euclidean or L2 distance, which is just taking the point's representation in the input space and the cluster center. With the cluster error defined, we can say that the entire quality of the clustering solution would be a sum of these errors. A problem here is that we know that minimizing the cost of the clustering quality is not a convex function and is known to be NP difficult. But we can come up with good approximations that approximate the optimal solution fairly well. One such algorithm is k-means, which is related to k-nearest neighbors. Let's take a look at how it works. Here we have a collection of data points on the xy plane having dimensions x1 and x2. And you can see here visually that it probably groups quite well into two separate clusters, one on the bottom left and one on the top right. And what we'd like to do is tell the algorithm, since we know that there are two clusters, to go find out the cluster membership of each point. We're going to do this by first introducing random cluster centers. For example, this red point here and this blue point. These are randomly chosen in the xy plane. Next, we're going to assign all of the points to the clusters by computing for any one point which cluster center is the closer one. For example, for this point here, we would make the comparison against this center as well as this center, and notice that this particular line is shorter, and hence associate this point as blue. Next, based on the points that were assigned to each cluster, we're going to recalculate the cluster centers. This is done by taking the average of all of the red and blue points and then finding the new location of the center of all of those points. So for example, this blue point here is calculated as the mean x1 and x2 coordinates for all of the various blue points that we have in the data set. We're going to iterate this again by assuming that now we have better cluster centroids, we can reassign the points to clusters. And so you can see what's going on is that the dividing line here is the plane where points that are equidistant between the blue and the red points is defined. So anything on the top part of this hyperplane would be considered a blue point, and vice versa for the red points below. We can then recalculate the cluster centers, and you can see it's starting to move to an optimal position where we have the blue points on the top right and the red points on the bottom left. We repeat this until convergence. By convergence, we have several different criteria, but one easy solution is to say when we iterate again and none of the points change their membership. This is the k-means algorithm at heart. It basically has two important steps: assigning examples and re-estimating centers. But let's go through it in more detail. First, we're going to start by taking the required input, k, which is the number of clusters that we want to divide our data set into. We're going to pick random centers anywhere in the grid that don't even have to be points in our data set. Then we're going to repeatedly re-estimate the point memberships as well as the location of these centers mu. We're going to do so until we're converged by using any number of stopping criteria, including the one that we talked about on the last slide. For the first step, what we're going to do is step through all the points in our data set, all m points, and we're going to calculate the membership y to a particular point j by looking at the one that has the minimal distance. Again, we can use L2 distance, like we've shown here, or any other measure to compute the difference between a point and the current location of the cluster center. We calculate all of these distances for all k centroids, and we take the minimum of that. We associate that point with that particular cluster's center. Once we've done this, this will have assigned all of the examples to a particular cluster. Next, we have to re-estimate the centers. We do this by going through all of the k centers and recalculating where the center is for that cluster. To calculate mu k, we're going to go through all of the points that have a membership in that cluster, sum up their values, and divide through the total number of points. We're going to repeat this loop as many times as necessary until we converge. And then, once we're finished, we have all of the labels for all of the m points, and we'll return that. Notice here that our y's don't have actual semantic labels. They're just cluster memberships. So even though cluster number 1 might be associated with oranges and cluster number 2 with apples, our clustering algorithm has no idea of the labels for these, and it's just returning an enumerated class label for each of these clusters. So one question that we might ask is whether k-means does always converge. So we'd like to have some type of proof of convergence. Well, let's scan through this algorithm and see where things are changing. In particular, we are going to stop when we have converged, which means that our cost function has become stationary and not changing. So where does the cost change? There's actually only two lines here that matter. This line, where we reassign examples to cluster centers, and this line, where we re-estimate the centers. Both of these affect the cost because the first line changes the membership of the point to a cluster, and the second line changes the placement of the cluster and hence the computation of the cost. What we want to show is that these two lines can only decrease the overall cost. We'll start by saying that the overall cost j plus starts with some value after initialization, where we first assign points to clusters, and we have a calculation of the distance of the points to their nearest cluster, and is lower bounded by 0 in the case where for each point the cluster center is exactly the same place as the point itself. Secondly, as y is a discrete label, it has to be from the enumerated set of k centroids. There can only be a finite number of steps if each step can only decrease the clustering cost. We can see that line A actually updates the cost only when the inequality holds. That means the new center k at time t is going to be closer than the center at the previous time step. So definitely this inequality enforces the fact that we can only either maintain J class or decrease it. How about line B? Line B is a little bit more complicated, but not much more than that. We can see that since each of the centroids, mu k, is calculated by the mean, it must minimize the mean squared error between the points and the center by virtue of the definition of the mean. Hence, both of these steps can only update jclust in a way that's minimizing the cost function. And because there's only a finite number of steps that can be made, we end up with a proof of convergence.